la bienvenida al cuarto simposio de geoamenazas. El día de hoy tenemos una agenda bastante entretenida, vamos a tener muchos programas diferentes. Esos programas fueron pensados para cada uno de ustedes. Estuvimos con los muchachos del grupo de Geohazard organizando durante todas estas semanas una programación que fuera entretenida y que fuera útil. Francis Bacon dijo una vez: el conocimiento es poder. Eso es importante en el lugar en el que estamos porque vivimos en un entorno en el que cada vez la necesidad de conocer acerca de la geología y la gestión de las geoamenazas es más inminente. A medida que va pasando el tiempo, las poblaciones crecen. Medellín es una ciudad que está altamente poblada y dado que no pudimos ocupar el valle, comenzamos a ocupar las laderas y eso implica que vivimos en una zona de riesgo constante. Eso hace necesario que el estudio de las geoamenazas sea cada vez más necesario y más eficiente. El día de hoy vamos a tener varias presentaciones y las estamos pensando con el fin de que podamos conocer entre todos qué tipos de estudios se están haciendo en geoamenaza, qué tipos de proyectos, cómo está avanzando la ciencia, qué labores están haciendo nuestros compañeros y cómo podemos compartir esos conocimientos para hacer crecer nuestra capacidad cada vez más. Colombia es un país que registra aproximadamente 5.000 movimientos en masa al año, y esta cifra no solamente es un dato estadístico, sino que es un dato que nos dice, bueno, vivimos en un país que está en el trópico, un país en el que pasan muchos desastres, un país en el que hay avenidas torrenciales, deslizamientos, un país en que las precipitaciones son extremadamente altas, en que los suelos se meteorizan muy rápido, en el que cada vez estamos más expuestos al peligro. Y ese peligro es para las personas que habitan el territorio. Nuestra labor no es solamente una labor científica, sino que es una labor que está estrechamente ligada con la vida de las personas. Y por eso este simposio es extremadamente importante porque nos va a ayudar a conocer cómo el estudio de la geoamenaza nos puede ayudar a cuidar la vida nuestra y la vida de las personas que nos rodean. Medellín, que es el lugar en el que se está desarrollando este evento, es una ciudad que, por lo que vimos la temporada de lluvias pasadas y por lo que hemos visto durante este año, sufre mucho de problemas de geoamenazas. Entonces aquí hay muchos deslizamientos, hay personas que están ubicadas en lugares que no son adecuados, hay procesos que afectan el comportamiento de las laderas, hay actividades antrópicas que nos ponen a nosotros y a las personas que están a nuestro alrededor en riesgo, y por eso, nuevamente, el marco de este simposio es importante. Vamos a iniciar con una presentación. Vamos a iniciar con la presentación del profesor Luigi Lombardo. Él es un experto en geoamenazas que nos está acompañando. Desafortunadamente, pues no pude estar aquí por un problema, estos problemas que siempre surgen, no logró conseguir la visa a tiempo, pero nos va a acompañar desde la distancia.
Así es, Ezequiel. Nuevamente bienvenidos todos los participantes. Este simposio reúne 3 sectores que pocas veces dialogan de manera directa. El primero, la academia, con expertos nacionales e internacionales que están actualizando los enfoques con los que se entienden las amenazas. El segundo, el sector público, que diariamente se enfrenta a estos desafíos en sus labores técnicas y operativas. Y el tercero, el sector privado, donde se implementan soluciones concretas desde la formación universitaria hacia la acción profesional. Hoy conoceremos cómo la inteligencia artificial puede contribuir a la predicción de deslizamientos, cómo los satélites permiten observar desplazamientos mínimos del terreno y cómo los años de experiencia y el trabajo articulado en el territorio pueden guiar políticas públicas más eficaces. Bienvenidos.
De acuerdo, hoy nos acompaña desde los Países Bajos el profesor Luigi Lombardo, profesor asociado de la Universidad de Twente, doctorado, que es geólogo con maestría de doctorado en la Universidad de Palermo, Italia, estudios de postdoctorados en la Universidad de King Abdul en Arabia Saudita. Recientemente fue incluido en el ranking de la Universidad de Stanford entre el 2% de los científicos con mayor impacto a nivel global. Su trabajo abarca no solamente los movimientos en masa, sino también las inundaciones, los incendios, los fenómenos compuestos y de múltiple amenaza. Bien, entonces, como les comenté, el profesor Luigi Lombardo nos iba a acompañar presencialmente. Tuvimos algunos problemas con el visado, no se pudo dar esa situación, pero logramos por medio de la tecnología, que es un amigo confiable cuando se usa de forma adecuada, tenerlo aquí presente con nosotros. Entonces, le vamos a dar la oportunidad al profesor Luigi Lombardo para que nos comparta su presentación, que es la primera ponencia del día de hoy. Bienvenidos.
Hola. 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 Can you see my presentation, first of all? Hello? Can you hear me?
Yes, teacher.
You can hear me, right? And can you see the presentation?
No.
Whoa, this is not good.
One moment, please.
Okay, it says I am sharing. It says I am sharing. I can see my face. I can see the room with all the red chairs. And I can see I am sharing as well. There are 3 screens. I can see I'm sharing. Very weird. Are you sure you cannot? Maybe you can select another screen from the app, because I can see all the 3.
Yeah, I think that we are going to do it, Luigi. Don't worry. It's, as you say, it's in another screen, yeah. Just 1 second. Yeah, Luigi, we are watching your screen. Thank you so much.
No worries. Okay. When Edien asked me to present on the future of landslide susceptibility, first of all, do I need to stop? Is there a translator, or can I do everything in one go in English? What? Edien? Can I do everything in English?
Yeah, in English.
Okay. So when Edien asked me to present something on the future of landslide susceptibility, I have to say that I have a sort of relationship of love and hate with the term susceptibility. So I basically wrote a title like, aren't we already in the future? So today I will show you a little bit about how this branch of landslide research evolved in the last 50 years and how we reached today and what are the challenges today, okay? So can you still see me, right? Please stop me if there are any technical problems. So the first question, I want to start from the very beginning. So I think that the first document that you can find of a landslide susceptibility map goes back to 1972. And it's a document from the United States Geological Survey made by BRAB. And if you type BRAB 1972, you will still find the same map online in the USGS portal. And basically what susceptibility was at the time, it started to basically classify or recognize areas across the landscape that were likely to experience landsliding, with several classes from no susceptibility to low, to medium to high susceptibility, okay? Let's fast forward, let's say a few years, actually 15 years from 1972, where in Paris, let's say, we had the first definition of landslide hazard. And landslide hazard at that point, you may know, of course, it's the work of Barnes and the committee. They published the first definition of hazard, where the susceptibility corresponded to the probability of occurring at least one landslide within a given mapping unit. So the susceptibility was one of 3 terms of the hazard definition pertaining to the spatial probability of landslide occurrence. Then we have a second definition, which is the temporal probability of landslide occurrence and the intensity term as well. All the three combined will lead to satisfy the hazard definition. However, what happened? It happened that susceptibility became quite prominent. Temporal probability, not to the same extent, but is also a major area of research. And actually, landslide intensity or magnitude at the time was much less explored. So for today, I will start by looking into these two terms, basically spatial and temporal probability, but highlighting the fact that these actually grew completely separate. So for 50 years, we had that essentially susceptibility and temporal probability were not modeled together, or technically were not modeled jointly. And this has done something very damaging, at least, okay, with the knowledge of today, which essentially the trigger of landslides, like a rainfall or a strong rainfall event or a strong earthquake, are modeled in a separate way from the spatial probability of landslides, okay, from the susceptibility. Actually, I have to correct myself, because in the case of earthquake, because earthquake are so difficult to predict, we cannot predict the temporal probability of earthquakes. Actually, let's say the term related to the coseismic landsliding developed in a separate and evolved in a different direction, a slightly different direction. But when it comes to rainfall-induced landslide, we indeed have a situation where for 50 years, researchers modeled the rainfall threshold, developed early warning systems that were only looking at rainfall data, and researchers were working in susceptibility separately from that. So we had a situation exactly like this. I put it in black and white because it was really black and white. Those that work on susceptibility and those that were working on rainfall threshold for temporal probability of the landsliding, purely linked to rainfall, with the term of rainfall duration and intensity expressing, let's say, the foundation for the definition of the thresholds. Whereas for the susceptibility, we had the use of terrain attributes, of geology, then derivatives that would control the spatial dimension of the landslide prediction. Now, my point that I've been, let's say, making for a while is that why do we have to treat these two terms separately? In the end, it's a multidimensional problem. Here I use the cube just to have it, let's say, to bring the perception of having space and time as well. And in the end, what we have is that the spatial dimension defines the probability of landslide occurrences. But actually, we should start to think that this probability changes both in space and in time. Every day, we may have a different probability of landslide occurrence that is also spatially characterized. Okay, so what I will present today is actually some of the research done to do spatiotemporal prediction of landslide, not only spatial. Okay, and the problem is that if we look at the research that has been done for 50 years, this has helped really a lot in understanding how do we divide space or spatial unit or mapping unit to define the spatial probability of landslide occurrence. And what happens is that if we take a single element of this space-time cube or space-time data, what happens is the spatial dimension is typically defined over pixels. Very often you see a pixelized susceptibility map. Sometimes you find slope unit-based susceptibility maps, or for larger territories, you may find also partitioning these areas into catchment. And for each one of these single mapping unit, we tailor-made a susceptibility model that will assign a probability of landslide occurrence. But if we want to really move to predicting in space and in time together, then the question is, how do we define a temporal unit Like we define easily space, but how do we find time? And the answer is it depends on the purpose. It depends on what we need and what we want to do. For early warning purposes, most likely you need to define time in a very narrow time window, an hour or a day. But for master planning purposes, to build a nuclear facility, we would need a place that is definitely stable. We cannot risk placing something on an unstable slope. So we need to do some prediction that would look into much longer time frames in the order of years or multiple years. So basically what I look always when I look at landslide prediction in space and time, I see something like this, that we have some sort of rubric cubes with the capacity of dividing time in different ways. Years, months, days, whatever. And today I will present some of the opportunities that are possible to implement and achieve. I will start from, let's say, a simple representation. Maybe I can zoom in. Hopefully it's a bit easier. So these are 30 years of debris flows occurrences in China. And I worked in here to implement a space-time debris flow prediction model where we defined, again, a mapping unit to be the catchment, but also in time, we defined the prediction over a year, so of every year. And then we can easily, for instance, transform such models into long-term simulators, because once you have fitted your model, then you can always predict what may happen in the future by changing the predictors. In this case, the most easy predictor to think of is, for instance, rainfall. You can plug in rainfall estimate for climate projections and then predict in the future. Until now, I have showed you China, but there are other examples that I've worked on. So this is a similar experiment where we modeled 16 years of Taiwan rainfall-induced landslides. And what you see is the same. What we obtained was spatially varying probability, but also temporary varying probability, all modeled within the same model. And these two examples are long-term predictions, right? These are the temporal units that I have used here. Let's say the student that I work with have used are years. But again, for problems much more close to our lives, in the short term, we would need something on a daily basis, a probability that may change every day for the period of interest, where the rainfall that we use definitely needs to change. In that case, in the previous cases, we were using, for example, maximum or mean or standard deviation of the rainfall distributed over a year in a territory. And here we would definitely need some daily or hourly rainfall data. How does it work, though? Just to show, because this is not everybody is working on spatiotemporal landslide predictions. So I took a picture actually from a Colombian student, Mateo Moreno Zapata, actually from Medellin, and then he came here to work with us. He did a PhD together with me. And here he implemented space-time prediction of landslides, in which this prediction is controlled by some factors, some predictors that you may know, geology or terrain attributes, that stays the same over time. But also he used some rainfall metrics. You see, you have triggering days, so 6 days before the rainfall event, we consider this rainfall the triggering rainfall, and then up to 25 days of preparatory precipitation whose cumulated effect may, let's say, change the predisposition of a slope to fail. And what he did here is essentially to extract the best combination between these two and define a model that would learn from the static predictors as well as from this rainfall distributed, let's see, on the accumulated of the second day and the accumulated of the 15th day. This is basically matching the concept of intensity duration that is traditional for rainfall thresholds, but in this case is part of the same identical model of the susceptibility, okay? Just changes in space and time. And to make it a bit more clearly, what you can see here is that Matteo implemented some predictors that you can see do not change at the scale of human lives. How steep is the slope, how concave it is, how forested it is, the lithology of it, and so on and so forth. But added to that, also, you see these are the same as before, added to that also some preparatory precipitation, some triggering precipitation, and the period of the year to capture some cyclicity. So this is some of the progress that susceptibility has made in recent years. So from a pure spatial connotation to a spatio-temporal connotation. But there is something that I showed you that Matteo did. So these are unique values of rainfall. So these are rainfall aggregated for a specific day of interest. So for a specific slope, let's say located in this point of the map, we measure that the cumulative at the second day is 100 millimeters, and over 15 days is 300 millimeters. These are two single values, okay? The interesting thing, I did something wrong, 1 second. The interesting thing is that you all have a phone, you all have some sort of AI at home. And the way the principle of these AIs are built is that you can talk to this intelligence, and the intelligence will decode your words. So it will take the continuous series of your voice and process that information as a whole. So what I thought a few years ago was to borrow this technology and test it for landslide prediction. Instead of using single values, I tried to implement this type of speech recognition algorithms to pass time series of rainfall, the entire signal, and then make a prediction upon this. And what you see here is that, for instance, this is a performance plot. And then you have that this is the traditional method that takes only a single value. And this is instead in black, the method I proposed, actually, that was authored by a student, Fan, that instead tested passing the entire time series to the model. And the difference in performances are very, very, very drastic. And this is one of the things that, yes, it's still academic, it's still an academic exercise, but this technology is very, very available. It's very, very available. We can transform this into a proper early warning system, into an operational early warning system very easily. It's just a matter of data availability and commitment to work on this, okay? So to continue and to give you some other representation of this, Mateo Moreno Zapata, I'm bringing up this Colombian example because he's one of the best students I've worked with, and I wanted to make it, let's say, make the audience proud of a fellow Colombian. And Mateo not only did the experiment before using single values, scalar values, but also used continuous signals in his work. And the cool thing is that these type of models capture also lagged effect. As you will see to the right, this is the rainfall, and this is the probability of landslide occurrence, so susceptibility. Here is raining a lot, but the probability is not changing. Only after a while, the probability starts to grow. And this is quite interesting because passing the signal to the model naturally captures also this lagged effect. And this I consider also a reason why not only we should move from space to space-time, but also within the space-time, I think the speech recognition type of models are the future that we should follow as a community. I will go back a bit one step before, because until now, I showed you examples of susceptibility, right? I showed you examples of models that defined probability of occurrence of landslides. And I combined space and time together. But if we think back at what Barnes defined with the Committee of Hague in Paris in 1986, they defined hazard also with a third element, which was the intensity. It is the intensity element or the magnitude, depending on how you read it more or let's say rigorously. And I will show you the other ways that we can nowadays also model intensity, okay? So what you will see here is a stupid example just to practically say that artificial intelligence nowadays supports us in doing this model very efficiently. We can easily discriminate stable and unstable slopes, right? This is a task that is typically a binary classification and separates green from blue, stable from unstable, the same algorithms. But in machine learning, we have classification abilities, but also regression. So what you see here is exactly this example in green and blue. And now what I would like to mention to you is that intensity is not the probability of a landslide occurrences, yes or no, in a given mapping unit, but it's rather the level of threat that a landslide, let's say, brings to an object exposed to that moving mass. So how do we define level of threats? For debris flows, it could be a velocity. For other type of landslide, but also for debris flow, it could be their volume or their total area, as the area is a proxy for volume. And these are all continuous properties. So instead of looking into classification like we did for susceptibility, intensity could be modeled in a very easy way, in a very similar way, but moving into regression problems. And what you see here is that this is an example. Please focus only on one triplet, this blue. These are two earthquakes I tested this method because instead of using a classification, here I used a Poisson regression model to predict not only where, but also how many landslides may occur within a slope unit, within a catchment, or within an administrative unit for an earthquake in Lushan or for the Wenchuan earthquake in 2008. So this is one of the possibilities to model intensity. Or here, this is a model. Instead of predicting how many landslides through a Poisson regression, here this model predicts the landslide planimetric extent. So how large the landslide is. So in meters squared, as you can see here. And, And this type of models are good to actually complement the information that the susceptibility looks, because the susceptibility tells you the probability that a slope may actually fail, but this type of models will tell you, well, if it fails, how large of a landslide do we expect? Okay, so this is a bit what I wanted to show you, let's say, the progress that we have taken. And now I will tell you a little bit more about what we can do more now that we have this intensity component available for us to model. So in reality, we can also combine susceptibility and intensity. Okay, so what you see here is the island of Dominica in the Caribbean. And here we predicted on the left, it's the mean susceptibility. So it's the mean probability of landslide occurrence. And here we predicted the mean area. So on average, how large a landslide would be if it would trigger for every slope. So this is already a much more informative model because it will tell us, I'm going to zoom only on one, it will tell us not only, again, the probability of a landslide occurring, but also how large we expect that landslide to be. And then we can create this type of exceedance probability maps that will tell you, for instance, that this slope here is not only quite likely to fail, but also to fail with a large landslide. Okay, oh, sorry. And then here, I will actually briefly mention, because I don't know if Ashok will present something related to this, but I wanted to mention that we said that we can use susceptibility, that we can use intensity, which is actually, this is a rock curve for susceptibility. This is a QQ plot for the prediction of landslide area. And we can also model this in space and in time. This is actually, for me, the best article, the best application that I have ever seen, let's say, in my career so far. And I have to say thank you to Ashok, which is there. So you go and ask him. But this is actually a true definition of landslide hazard, because it predicts where, it predicts when, and it predicts how large a landslide may be in all this space-time cube. And once you do it, you can also project this for return periods, and then basically estimating location that will grow susceptibility and intensity jointly. So hazard for certain return periods of the main trigger and of the landslide distribution itself. So what if now I showed you another potential direction that I consider quite valuable, which is actually susceptibility and exposure together to assess risk? Because what we can do here is we have looked at spatial models, right? We have looked at spatial temporal models, but we can do this in combination with actually the thing that we care for. Because if a landslide happens in the middle of the mountains where nobody is there, also nobody will care. But if it happens on a major road where trucks are passing through, because Colombia, for instance, has a crucial role of truck bringing goods across mountains, then this is actually one of the things that we need to look at much more carefully. And in doing so, we also have the chance of including temporal probability in this. So for instance, here you see a model that we developed for Europe, for all the mountain belts of Europe, where we combined the probability of landslide occurrence, so susceptibility, together with the potential monetary value of that specific piece of land. Then we also did some combination with people that may be affected. Because during the day, if we have a population distribution, you can assume that during the day we all go to work, so residential areas will be more empty. But during the night, we go to sleep. So residential areas will be full, and vice versa with respect to offices. So we can look at the problem looking at monetary value, but also we can look at potential victims exposed to landsliding. And this could be done in space, like you saw here. This is a static map for Europe. But because I like space-time, this could be done also for every year of our interest. This is simulations for 2022, 2023, 2024, and so on until 2030. Why? Because on one side, we have rainfall projections. We have also building areas, by the way. So building projections, how much a city will probably grow according to the land use plan done for it. And then combining this information of spatial and temporal probability of occurrence with the expected growth of an urban area, we can also assess long-term risk. I will close here, basically in terms of future, because for me, the future is also open. Here at ITC, everything we do it open source. And I have also had the pleasure to work with another student, now also professor, Giacomo Titti, who is developing plugins for QGIS. And there, for example, everything I presented today is sort of available: spatial, temporal, susceptibility, intensity predictions, all at a click of your mouse. So in that sense, I quite value that these are tools that can, let's say, help make these things happen and become operational. That's it. I will just say that whatever I presented until now, it's it's mine because these are my ideas or partially my ideas, but they are not mine alone. They come from a big network across the world, and Colombia is part of it, although it's not in that map because I don't have a formal publication with Colombian colleagues, but Elie is a close friend. But aside from this, I wanted to mention let's say, two more people other than me, because these are the closest collaborators I have. These are also my friends, and therefore I wouldn't feel right to talk about this without mentioning their names. One is Hakan Tanyash. We have been working together since 2017. So he's basically my twin in terms of research. And he is probably the most hardworking person I know, capable of working 24 hours per day for his entire existence. It's impossible to compare against. And Ashok, who's there instead of me, luckily he could come instead of me, who's one of the brightest talent that I have known so far in an entire career when it comes to landslide research. He will be making breakthroughs that we should all look forward to. So that's it. I just wanted to let's say close like this, and thank you for your attention. And the remaining time, I thought we could have some question addressed, and I can easily answer them. Okay. Thank you. Hola. Hola. I can also stop sharing, by the way, now, I think. Hello. Wow, the room is much more full now.
Agradecemos al doctor Lombardo por su participación y esperamos poder contar con su presencia en nuestra ciudad y en nuestra facultad en una próxima ocasión. Resulta clave entender cómo la ciencia ha transitado de la pregunta ¿dónde puede ocurrir? Hacia ¿cuándo y cómo ocurrirá? Esta evolución del análisis estático al dinámico es fundamental en territorios de alta complejidad geológica como el nuestro.
Buenas. Le damos muchas gracias al profesor por su presentación, verdaderamente muy interesante. Hoy aprendimos que los modelos de amenaza ya no son unos modelos simplemente estáticos, que uno hace un modelo de amenaza, le pone una configuración de tiempo y ese es el modelo de amenaza, el vaya a burrar para los próximos 20 años, sino que son modelos que pueden avanzar con el tiempo e incluso están a nivel de horas, modelos que van evolucionando. O sea, ya hoy en día es imposible pensar en un mapa que se imprima. O sea, un mapa de amenaza no puede ser solamente un mapa impreso, un mapa estático, porque la amenaza va cambiando en función del tiempo y el riesgo va cambiando en función del tiempo. Como mencionaba el profesor, es demasiado importante entender que la amenaza no solamente es para... La amenaza no solamente es para el lugar en el que ocurre, sino que está relacionado con las personas a las que puede afectar. Entonces, un modelo correcto de amenaza tiene que involucrar el riesgo, porque a nosotros lo que nos interesa es saber qué personas están en ese lugar y cómo les puede afectar el evento que va a ocurrir. Entonces, súper interesante que el profesor haya diseñado modelos de amenaza que funcionan con la probabilidad temporal, con la probabilidad espacial, con la probabilidad temporal, pero también en función de qué personas van a ser afectadas por eso. Y que utilice la inteligencia artificial no solamente para preguntarle a ChatGPT qué voy a comer hoy, sino para hacer cosas mucho más interesantes como son estos modelos. Vamos a hacer en los siguientes minutos que nos quedan, en el resto del tiempo, vamos a hacer una sesión de preguntas. Las personas que tengan preguntas para el profesor las vamos a transmitir y vamos a ver si logramos que él nos las responda y las podamos comunicar a través de estos aparatos. Entonces, ¿quién tiene preguntas? ¿Alguna pregunta sobre la presentación del profesor? Vamos a...
Hello, Luigi. Are you hearing?
I can hear you fine.
Okay. Thank you for the presentation, first of all. My question is, you add the temporal variable precipitation to this susceptibility model, but
Yeah.
context here in the metropolitan valley, we have some problems with the evolutions of the people. I mean, the population here is so fast, it's growing so fast, yeah. So I would like to know how to these social variables enter in this type of models, just in, I mean, talking in susceptibility, like the evolution of the, I don't know, in a place that before there is not water or water resource. Now in 5 years we have a population here that needs water. So some business install a pipe, and this risk of the pipe could cause another landslides. So there is, I don't know, a future models or another options to integrate these social variables in these susceptibility models. Thank you.
Can you hear me right again? I think so. Nothing changed. So, yes. I mean, it's a super relevant and interesting question. So the thing is that these types of models, they're typically covering large areas, right? As they cover large areas, it's very difficult to introduce the information of super highly detailed occurrences, right? Or let's say spatially varying variables. For instance, a pipe. You mentioned a pipe. Well, if you could define every new pipe that has been, let's say, put into place into the model could learn, let's say, the role of the pipes. The problem here it is that these artificial intelligence, let's call it this way, of this data-driven models, they need to learn from past events to be able to make correct predictions, right? And in this sense, if you think about it, we would need to not only have a distribution of, let's say, pipes, let's call it this way, today or tomorrow to generate suitable predictions, but we should also be able to express the same information for past events to be able to train these models, which is, I think, really major challenge. You could use population density as a proxy. But then the problem here is that population density may be a very biased predictor. You could have maybe richer areas that have the money to do the work properly, to hire an engineer that would not make mistakes, and poorer areas may be less capable of doing the same, and then they, let's say, they are not careful enough, let's put it this way. And therefore, if you use just a general property called the population density, you will actually lose that information. You will mix the two. So it's a very, very tricky information to address. What I could answer is these models learn from past events, from data that you feed them. As long as you are able to characterize, let's say, spatial and temporal distribution of, let's say, man-made disturbances to slopes, the model could learn, and therefore it would be able to integrate those. I find it a very big challenge. Maybe collaborating with local geotechnical engineers that did the work could be a way, and then building a database of all these, let's say, projects could be a way to describe these intervention on a slope for to sustain urban growth and their effect to landslides. I will close also my answer by saying the problem here is also double, because the same problem of population density that would potentially stress the slopes is also a problem that you can turn around and say, how do I then define how much the slopes would be stressing or would be contributing to the risk of the population? Because what do you want to do? Basically, you can insert a variable population density to basically capture what you were mentioning, but then the risk assessment will not work very well, at least. So I would say the best solution that I think is to build a database for this, and maybe coordinating with local geological surveys, with local companies, and then see if they want to share the location of their work, and we start from there. I'm not sure if there would be any company that would like to share their own location of their work, because if then the models will demonstrate a sort of causality with the landslide occurrences, it may not be beneficial to them. But I would start from there. Yeah, I finished my reply, by the way.
Andrei Torres por acá. Quería saber si de pronto has tenido la oportunidad de validar estos modelos predictivos con información de formación del terreno, como la que se puede conseguir con INSAR o con otra instrumentación.
I understood it in Spanish, no problem. I understand 100%, I speak 0, so no need for translation. Was that all the question? Can I address it? I think so. So validation of these types of models, definitely possible. The problem with INSAR is that INSAR is a very good tool, but at the same time, it monitors slow movements, right? So it looks at coherence between two consecutive acquisitions, and then on the basis of that, estimates deformation. But landslide can be very fast. So if they are fast, we will lose coherence. And then maybe in the time series of let's say, of a slope that is moving, when the coherence is completely lost, it means there is a landslide. And that could be a way to validate these models. Another way to validate these models would be, for instance, instead of looking into SAR images, to look into optical, for instance, and do some semi-automated mapping on a regular basis. And then as we predict for next week or in 2 weeks, we can also use a posterior whatever image has been captured by satellite, by optical satellite, generate an inventory and see if their inventory matches our prediction. So yeah, of course we can validate them.
¿Aló? Muchas gracias por la presentación. Nosotros aquí en Colombia hemos hecho algunos trabajos como con una tendencia a la predicción y al conocimiento de los lugares donde se pueden presentar deslizamientos por causas diferentes. Entre toda la información que usted nos presentó, no vi algo que tuviese que ver con una información que actualmente se está utilizando en otras partes, que es la información geofísica superficial a partir de la gamma espectrometría aérea. Nuestro trabajo acá lo hicimos en una zona donde hubo un deslizamiento el año pasado en Chocó, por causa que el detonante fue la lluvia. Hicimos una cartografía a partir de gamma espectrometría y luego la comparamos con imágenes que ya, digamos, predictivas, donde se podía evidenciar y conocer sí había una coincidencia y dicha coincidencia fue bastante alta. Entonces estuvimos investigando y nos dimos cuenta que esa aplicación con esa herramienta se está prácticamente comenzando a dar y principalmente porque gran parte de toda esta situación de deslizamientos tiene que ver con la geología. Nosotros no tenemos en algunas áreas una cartografía buena, pero no solo la gamma espectrometría que mide los 50 centímetros más superficiales es la que nos daría un aporte para conocer esos cambios litológicos y posibilidades de demarcar situaciones o lugares donde hay susceptibilidad de deslizamientos, sino que lo combinamos también con geofísica de subsuelo, la cual nos indicó que hay zonas susceptibles por causa de fallamiento. Entonces, nosotros tenemos por ahí una presentación, si de pronto nos dan la oportunidad de que se la mostremos para que la conozcan y la podamos pues como palpar un poco y sentir que es una opción también de ayuda. Gracias.
Can I reply? Can I reply or not? I don't know if I am still muted or not. Can you hear me? Yes or no? Can you hear me?
Yes.
Oh, okay. Super interesting question. So gamma spectrometry, how do we use it? Well, you answered almost in your question. Definitely, I consider it a very valuable source of information, especially like you said, if the geological map is not very detailed and there are no geological map that can compare. Of course, if you have a 50 centimeter resolution, we don't have a typically geological maps would be 1 to 25,000, one of the best that you can get for very small sectors, most likely. So I consider it a super valuable source of information. What I would highlight is that this will help the model to substitute or complement the geological description of the study area, of course. So it will be able to characterize more spatially the model. But what I am guessing is that either you don't have systematic acquisitions of this measurement in time, or in any case, you will not have it predictions for the future. So I would value this information a lot, but for the spatial information it introduces to the model, I would not really value it from the temporal characteristics that it will bring, because what I am guessing is that will be a single map, let's say. But other than this, I consider it a very valuable additional source of information, another valuable predictor. And if I am wrong, and then you can have also repeated acquisition, and you have also forecast, I am also happy to revise my answer.
Okay, thanks, Professor. I have two questions. I think they are short. The first one is how physical models and what kind of are integrated in these probabilistic prediction models. And the second question is, what are the next steps or problematics that need to be addressed in this field?
Okay, physical models. Nothing I have presented in reality expressively includes physics in it. So these are models that are inspired or that well overlap with the concept of artificial intelligence, as you may have been exposed to in normal life. This being said, and actually, again, Ashok will be there among you, or go and listen to his presentation and ask him questions, because part of his professorship here at the University of Twente, he's specifically, or part of it is specifically meant to address the problem of introducing physics into these artificial intelligent models. And actually, Ashok developed a model which is called physics-informed neural network. for landslide prediction. And in this case, my answer is nothing I presented formally includes physics. However, these new architectures, especially neural networks, you can now adapt them so that the loss function that they use to optimize, let's say, their predictions respects some laws of physics. So even though I did not present it, there are solutions for it already. What Ashok has done so far, he has worked for, let's say, earthquake-induced landslide, where he has validated these physics-informed neural networks. And the thing is that an earthquake happens in an instant, so, or approximately in an instant, let's pretend it this way. So you can compress time very easily. So the model of Ashok, the physics-informed neural network of Ashok, was mainly spatially distributed. The problem will become when the development of the physics-informed neural network will touch upon actually rainfall-induced landslide, where you have time series of rainfall over 30 days, and how do you pass that information to a physics-informed neural network? Because at that point, the physics will involve some complex differential equation, partial differential equations, and therefore, going back to your last question, where the challenge would be, actually would be to adapt this type of physics-informed architectures to handle spatiotemporal problems. You can ask him more. He is around there, so you can go check with him. He will tell you much more than I can.
Thank you, teacher. Muchas gracias a todos por las preguntas. Gracias al profesor por su presentación. Vamos a continuar con el evento para que no nos apremie el tiempo más adelante.